So let's record. How many people? 22 people. Okay, so here we have again an online lecture, but we'll see. So we looked at what we were doing maximum likelihood estimate, and we kind of stopped last time at the map estimate. We gave an example of how it is used. I mean, we've not covered it in very much detail, but you got an idea of how map estimate can be used and how map estimate is different from the ML estimate. Okay, so especially when you have data scarcity and all that, and imbalance of data in one particular class, then map estimate can sometimes be better than is usually better than the ML, just the plain ML estimate. So yeah, because typically in pattern recognition problems, we typically deal with large dimensional data. Your features are usually in high dimensional space. So because of that, you will always feel that data, more data is better. So in that sense, if there is scarcity of data, it is probably a map estimate will give you a better estimate. I mean, so this is true in practice. Okay. So today I wanted to start something else. So this is not from any particular book. I've been taking it. Eventually we will come to Bishop, but right now I'm covering some basic stuff which I want to just set the background. 26 people have come. I wanted to mention about the project. So okay, two things. How many of you? In today's lecture I want you to work out something. So how work out something means I want you to sit in front of paper and pen. Okay. So how many of you are going to do that? I mean, how many of you are? It's possible for how many of you to do that? If I ask you to do something, and even maybe once whatever you get, can you share the result by turning on your video so that you can show it to me on paper? So for how many people it is possible? Sharing, if turning on video is not possible, at least how many of you are able to interactively do something when I tell you today during this lecture? Please raise your hands. Yashwant, Ankit, Prachi, Ayush, Ajit. Okay. Okay. Not. I wonder what the others are doing. They're all lying down or something, or I don't know what. Okay, you can lower your hands. Thank you. Okay. One sec. Yeah, too much background noise. Okay, so how many people? 27 people. Okay, so just a point I wanted to make for the project. I'll write it down here so that later people will not complain. ROC question. Use the posterior probabilities. To compute the ROC. Not the likelihood. In the video, I have mentioned use the likelihood. So this is wrong. in the video. Okay, use posterior probabilities, not the likelihood. So the whatever thresholding you are doing, you have to do it on the posteriors, not on the likelihood. Only then will you get the expected result. If we were in person, I could have given you a little more motivation about the kind of features which we were using, but currently let's not do that. Okay, so I think you should get an ROC something like this. You should get, this is, let's say, the 45-degree line. You should get an ROC, I think, like this, some smooth curve for ROC, another smooth curve or something like this. This is for MFCC and this is for STE. Okay, this is the 45-degree line. This is your TPR. This is your FPR. So you should get something like this. Basically, your MFCC features are better at discriminating speech, non-speech than short-time energy features. That is what you should conclude. Okay, and your ROC should reflect that. So please do it. Okay, yeah, fine. Now let's come back to what I wanted to cover today. I wanted to cover a little bit on distance functions. Some of you are probably familiar with all this material. So especially if you're doing metrics theory or if you have done any course on analysis or something, you would have you'll probably be familiar. So I think most of the math students will already know this. In at metrics theory, at some point you will reach this, if not done this before. But this is nothing very difficult. Like I said, these are some things which you already. Yeah, sure. It's assignment 1, not project. Correct. For the assignment 1. Thanks for pointing out. Okay, yeah, thanks. All right, so we started this course with by using vector spaces, right? So we said we wanted a framework, a mathematical framework by which we can measure properties of vectors. So whatever we wanted to, whatever objects we are interested in, we are going to represent them as vectors in a vector space, and then we wanted to measure various things. Like for example, let's take for just because it is easy, we will take the vector space R2. So that means it's the basic 2D space. So if there were I had vectors here, one, I'll call this vector v1, I had a vector v2, and I had a vector v3. We wanted to be able to measure distance between the vectors, right? So that means so the distance measure, let's say some d of v1, v2, and then distance between v1 and v3, right? We wanted to be able to say that the distance between v1 and v3 is larger, let's say, than the distance between v1 and v2. So let me write the v1 here. So we wanted to say that this distance was more than this distance, right? And that the framework of the vector space gave us a mechanism, and we saw. Let's see this. Yeah, and but we have not explicitly looked at distance because most of the time we were using Euclidean distance. Like for example, if v1, v2, v3 are the three vectors, and okay, maybe it's not the okay, the components, let's say v1 in this is a 2D case. Let me call it x1, y1. These are the components, and v2 was x2, y2. We were mostly using, so when we wanted to find the distance between v1 and v2, what was the distance which we used? We are basically using the distance between, like this was basically the distance which we use, x1 minus x2 the whole square plus y1 minus y2 the whole square, right? But before, so this was the standard distance which we used, and this was the Euclidean distance. But before we come to the distance itself, we should look at what is this? What is this? Okay, let us look at a more general definition of an inner product. Okay, so in this, an inner product between x and y, we write it like this, and the inner product induces the norm given by this. This is the induced norm. So this norm, this is the norm induced by the inner product. So most of the time when we were dealing with RD, the inner product, we saw it in a more restricted form, which was the dot product, right? So for example, what was the, so for example, if we had two vectors, x and y, x dot y we said was x1 y1 plus x2 y2 plus xd yd. Okay, so our that means our x is x1, x2 up to xd. Okay, so this was the dot product which we were looking at. And what is the induced norm here? So if you look at the norm induced by the dot product, this is nothing but dot product of x dot x, which is nothing but your x1 square plus x2 square plus xd square, which is nothing but your Euclidean distance. Euclidean distance from origin. Right? Essentially, the norm of the vector basically tells you, gives you its length, or that is equivalent to the distance from the origin. Okay, but there could be other distances. Why should we restrict it to only this distance? Many types of distances are there. For example, let's say, let me see if I can open it here. Let's say if you go to New York. Okay, let's say you go to New York. This is a map of Manhattan. Okay, so Manhattan has this famous grid-like structure. The streets of Manhattan have a grid, completely a grid. So there are these are the long ones are avenues, and across the island there are streets. So for example, if you want to go from, let's say, Chelsea Market to Flatiron building is a landmark in New York. So suppose you want to go from here to here. Okay, what distance will you use here? Can you use the Euclidean distance? You can consider this to be L2 space. I mean, you can consider this to be the x2 space in the 2D plane, right? Because we are doing it on flat land, let's say, assuming that it is fully flat. So how will you find the distance between Chelsea Market and Flatiron? Can you use Euclidean distance here? Yes, somebody has to say something.
So we can take 3 points.
You can take
3 points and then use Euclidean distance.
what point?
So we can take 3 points, the Chelsea market, the building, and the third point, that is the corner
No,
of
that
the building.
distance is always computed between 2
So
points. Why do
then
you want a
only we
third point?
can get the exact distance of the blue mark.
No, no. You're saying something which is generally correct, but that is not the answer I'm looking for. What is the
Directly
correct
we
answer?
can't use Euclidean distance.
Yeah, because if you use Euclidean distance, it is basically the distance between. It is going to be this distance, this straight line distance between Chelsea Market across all these buildings and across all these streets, and directly to flat end. So that kind of distance is not possible here. Okay, because the space which you are does not allow you to do that because there are buildings in between. So you have to go like this. You have to go down this 15th Street. You go somewhere here, and in the 5th Avenue, you take a left, and then keep going straight, and then you'll hit the Flatiron Building. That is how you need to go, right? And what is this distance called? What is this distance? I'm sure many of you know it.
Displacement.
No, no. There's a name for this distance. Euclidean distance, I said it is not possible because you cannot go through the streets. You cannot, there are buildings here. Right? You have to go like this, go from here to here, and then from here to here. So what is this distance called? It's a very famous distance.
Sir, Manhattan distance.
It is a Manhattan distance. This is Manhattan only, and so that is why that Manhattan distance name came from here because it is applied to the streets of Manhattan. So there are so coming back to our boring text, Manhattan distance. So for example, if you have a grid like this, very bad drawing. So Manhattan distance, if you want to measure, let's say from this point to, let's say, a point here, you can either come like this and like this, or you can also do, let's say, from here to here, from here to here, from here to here, okay, then you go straight and then you reach here. Both of them will give you the same Manhattan distance. The blue as well as the red will give you the same Manhattan distance. Okay, so that is another type of distance. And so if you study it more formally, there are some properties which a distance function has to satisfy, and finally if it satisfies those properties, it can be called as a metric. Okay, and a vector space with an associated metric becomes a what is it called? It's called a metric space. Okay, and we have metric spaces. Okay, I mean we are considering it only. We are considering only real valued vectors. I mean the underlying field is R, and the vectors themselves are also R. So yeah, so this was one example of a distance. We'll see this distance once again. So coming back to what I was saying, this distance between these two vectors, or these v1 and v2 and v1 and v3, for example, it need not always be this distance. Based on the application you're trying to do, you can use various types of distances provided that is suitable for whatever you're trying to do. Okay, so you don't have to think only about Euclidean distance. So again, coming back to so that is why the inner product comes here, because inner product induces a norm, and from this norm you can get the distance. So this is what I said. I want you to try out something. Okay, now let me define inner product, which we saw till now was this inner product, right? Because this was basically the dot product, and this was the induced norm from it. But now I'll give you another inner product. Again, there are some properties which an inner product has to satisfy, but right now let us take two vectors u and v. The inner product between them I define as 2 u1 v1 plus 3 u2 v2. Okay, do you understand? Inner product between this, again we are dealing with two-dimensional space, and rather than using directly the dot product u1, rather than using directly the dot product, we are defining a new inner product between vectors. Okay, now what is the induced norm? What is the norm induced here? Induced by this inner product. Essentially, you have to compute induced norm u is equal to inner product of u with itself. Okay, so this will be nothing but 2 u1 square plus 3 u2 square. Okay, agree with me or not?
Yes, sir.
Yes, sir.
Okay, so before we do anything, so again let's come back to the, I should have done this earlier, standard inner product, or dot product, and what is the induced norm in that case? U is equal to u dot u dot u, which is equal to u1 square plus u2 square, square root of this. Okay, so this is, let me call this 1 and let me call this 2. Okay, so now this is what I want you to do. What is a unit circle? What is a unit circle? What is unit circle in this space? In this 2D space, what is the unit circle?
Radius is 1.
Yeah, it is, you can think of it as the locus of points, which has a, has the constant distance from the center, from the origin. So let this be the origin. So unit circle means at all points, the distance is going to be 1. Okay. So now draw the unit circle for 1, for this distance. Draw the unit circle for distance 1. This distance, this, yeah, draw. How will the unit circle look like? This is a 2D plane, so I have x and y coordinates. How will the unit circle look like? So basically, unit circle means I want the set all, it will be the set of x such that distance of x is equal to 1. Okay, and let my, yeah, sometimes I'm using u, sometimes I'm using x, so sorry about that. Let me call it x1, x2. This is my x. So draw the unit circle for x equal to 1. For this distance, for the first distance. How will it look like? So x equal to 1, or 1 is equal to, what is the distance? This we know. So this is the root of x1 square plus x2 square, which will give me I'll just write it here only. If I just take the square, 1 I will get x1 square plus x2 square. x1 square plus x2 square equal to 1. What is this?
Equation
What is
of
this equation?
circle's equation of one
Huh?
radius.
Sorry, what?
Circle's equation only, sir.
I cannot hear you.
Equation of circle.
It is an equation of a circle. Everybody agrees? It is basically just the equation of a circle which you have been seeing all along. I mean, in geometry you must have studied. Okay, this is not a very good circle, but this is the first circle. Now, what you have to do? What should you do next? What should you do next? What is the next question I'm asking you to do?
Circle for 2.
Yeah, draw the circle for the second distance. Yeah, now draw the circle with the second distance. How will it look like? What will be the intercept here? It's going to be 1. This also it's going to be 1. How will it look like? Can somebody show me?
Ellipse.
Why is it an ellipse?
Because
A.
in
Why
x1
is it an
direction,
ellipse? Right.
in
Go on.
in x1 direction, intercept is 0.5, and in x2 intercept is 0.33.
0.5. Is it 0.5? Are you getting 0.5? What is the equation
Yes,
of an ellipse? I think x square by a square plus y square by b square
b
equal to
square
1 or something. No?
y.
So
Yes,
point,
yes.
1 upon root 2.
0.707.
Right. So basically, in the L2, in the second distance, your equation will be x equal to 1, which is equal to root of 2. What did we write? 2x1 square plus 3x2 square. And so 1 is equal to 2x1 square plus 3x2 square. Okay, so if I take the root, I will get the equation of the ellipse. And I mean, again, it's not a great ellipse. So this will intercept at 1 by root 2. This is minus 1 by root 2. This is 1 by root 3. And this is minus 1 by root 3. So you can see how this is also a unit circle. Okay, this is circle with distance 2. Both are circles. The distance is constant from the center, from the origin. But based on the distance function you're using, the shape changes. Okay, so we have always been looking at Euclidean distance. So that is why the circle in our mind is a circle like this. But in general, it can have other shapes also. Okay. So some other examples of distance function. So both these distance function were induced from the inner product. This inner product had a particular form. This inner product had a different. This induced a different norm. But we can also define other. Not all distances are induced from are coming from the inner product, but there are other distance functions which we can measure. Let's say, for example, the sum norm. Just call this, which is nothing but V1 plus V2 plus Vd. This is the sum. This we can also have the max norm. Sometimes it's called the V infinity norm, which is nothing but the max. Okay. Which is the Manhattan distance? So see, there is a difference between the norm and the difference between the distance. Norm is typically for one vector. Distance is between two vectors. Keep that in mind. Okay, and equivalently, distance can also be defined as the norm between x minus y. So based on what norm you are using, you can measure various types of distances. Okay, so Manhattan distance is using the which norm? Yeah, you can do that as homework. And in fact, I would suggest that you should see. I mean, if you look at in general, you can see the LP norm, which is nothing but I goes from 1 to D. What is that? VI P, the whole of 1 by P. Okay, where P is greater than or equal to 1. Okay, so as homework, you can write a program, plot the unit circles for L1, L2, L4 norms. Okay, take it as a homework. So write a program. So write this and show how the circles look like. Okay, this is the general LP norm. So you can do that as a programming assignment. So how is all this relevant to us in pattern recognition? because we want to measure distance between feature vectors, right? Then based on what distance we are going to use, we will get a different result. So also there is one thing that there are different types of norms. So it can be shown that these norms are generally equivalent to this. So there is no big difference between them. I mean, they are all equivalent to some scale factor. But the properties which are given by some norms are useful to us than some other norms. So that is why we have various norms. Okay, that maybe we'll come to it at some point. Which norm to use? You should use the norm which is more suitable for the application you're targeting. Okay. So this brings us to till now we've been doing unsupervised classification. So now we can look at clustering, which is an unsupervised technique. That means the labels are not there with us. And standard method is the k-means clustering. So basically in k-means clustering, what do we want? We have some data points D. Let's say x1, x2 up to some xn. Xi belongs to Rd. Okay, these are all vectors. So now we want to divide this data into or separate this data into clusters. What do I mean by a cluster? What do I mean by a cluster? Yeah.
Group.
Anybody?
Group of features.
Group
Class,
of
class.
features. No.
Group
Cluster
of
need
samples.
not be a class.
Class with same features.
Group of points which were near to the like some of the points, like they make some kind of groups between them.
Yeah, I think what Yashwant is saying is probably the closest answer. Yes, so basically in a cluster, distance, I mean the points or the data points within a cluster have lesser distance between themselves than when compared to distance from a point outside the cluster. So that is why the distance, what we saw earlier, is important, because the whatever clustering you are going to do will depend on the distance, what kind of norm you are using. Okay, so if you do clustering with one kind of norm, you will get one result. If you do clustering with a different kind of norm, you will get a different result. So that is why the distance function is important. And so typically in k-means clustering, our objective is, given these n points, we want to group them into k clusters, and we are assuming that k is known. Somebody already tells you that there are k clusters. For example, I don't know if I don't have directly the image with me. Let me see if I can get up from here. I should have. One sec, hold on. Okay, can you see my screen? So this is an image. Can you guess what is this image? Somebody, can you guess what is this image? I'll show you one more example. Can you guess what is this image? Hello? Hello, are you there?
Yes, sir.
What is this image? Can you think? Somebody guess.
The cells.
Yeah, this is an image of cells under the microscope. This is a I think it is cytology images. Okay, so these are black and white images of cells under the microscope. So if you want to do clustering of this image data, suppose you have lots of examples like this, what should be K? How many clusters are there? What is the example given here? This image is an example. This, I said, no, there are data points x1 to xn. You can think of this x1 as a vector representing this entire image. This whatever 32 cross 33, some image. I don't know what it is. There image info. Yeah, it is 512 by 512 dimension. This image. Okay, so that 512 square. This can be made into a vector of size 512 square. I think 10 raised to 18 or something. No, I don't remember. Okay, 512 cross 512, 2 raised to 18. Yeah. 512 by 512 so you'll get a vector of size 512 square cross 1. So that is one vector which represents this image, and that is one of the x size. So how many clusters should this image have?
3.
3. What are the 3?
So the middle one, the left.
The nucleus of the image. This is the nucleus. Yes. Then
Uh,
so k is equal to k. That is the first k. What about the second k? What will be the second cluster?
so the lowermost in right.
The lowermost right. No. You are going to divide these images, this image into regions. Let's say we are not clustering within the. See, so maybe I should give you the context. Suppose you want to segment these images. You want to segment them. That means you want to determine the different components of the image. So you want to say, okay, I want to study the nuclei of all these images. So I will have 3 distinct clusters. One is the cluster containing all the nuclei. Second is the cluster containing the internal parts of the image. And third, maybe the background. So those are the 3 clusters. And when we get a new image, we want to divide that image into one of these 3 clusters. We want to basically divide them into the nucleus region, into the cell region, and the background. So those are the 3 clusters in this case.
So, but if we classify them as these clusters, then how do we use the distance functions that we studied right now?
No. The distance function is used in making the clusters. So basically, the cluster of nucleus means that all the points which represents the nucleus will be in one cluster. So the distance between this region and this region is going to be less than the distance between the nucleus region and, let's say, the cell body. That is basically what I meant.
Okay, sir.
Okay, but maybe we can, based on how much time we have, we can actually do the k-means clustering. So clustering here, I mean, if you want to segment the image into the different parts, the different components of the image, then we will divide each of these examples into 3 clusters. Okay, so I will stop here. Any questions in what we covered so far?
So in the plot that we have to draw the homework question, the norm, what should we take the value of p there? So what is like and
I've
get
given value. No,
so
L1 P is 1, 2, and 4.
what p is 1, 2, and 4.
LP,
Okay.
that is L1 norm, L2 norm, and L4 norm.
Okay.
I think you already. This is for some other norm. This is not the P norm, but this is. You will get unit circles in U. So this ellipse is not part of this. But basically, you have to repeat the same procedure.
Sir, how that is circle means equation is ellipse, no?
How?
How you are saying that that is a circle means
Ellipse.
ellipse? Yes, ellipse
Yes,
equation.
ellipse is a circle. That's what I'm saying. That is what I'm saying. Ellipse is a circle. Why do you say ellipse is not a circle?
Okay, okay, then that is not a unit circle, but it's type of circle.
No, it is unit circle. Ellipse is unit circle. You don't agree?
Sir, I am not able to understand.
What is the definition of a circle? Circle means, we said it is, have I written it here? No. Circle means, I said, it is a set of points which is equidistant from the origin.
Yes.
Okay. But I have not said which distance I'm using. I can use different distances. If I use L2 distance, my circle will be this standard circle which you are all familiar with.
Okay, okay.
If I use L1 distance, or not L1, if I use this distance which is induced by this inner product, this inner product is inducing this distance. If I use this distance, then my unit circle looks like this, because the distance in terms of this distance of each of these points is same from the origin.
Okay. Okay.
Okay.
Thank you, sir.
So the distance, how the circle will look like depends on what is the distance you are using.
Okay, thank you.
Yeah, so you'll see the different shapes of circles when you do L1, L2, and L4 unit circles. Okay, at least somebody asked some questions, which is good. Fine. Okay, I'll stop now. We will meet. I don't know when. Today is what? Today is Thursday, no? So next week, if the road opens, then we will meet. Otherwise, we'll continue online. Fine. Oh no, not next week. Next week is exam. No instruction week. We'll meet the week after. Okay. Yeah. Please come. Please do the assignment. I will not give you any extension. So please do it. Thank you. Bye.
Thank you, sir.
Sir, do we have a tutorial from 2 p.m.?